We can hear you. So the next talk is on the security of some crypto systems based on subfield images of codes. And the talk is given by Kirill Vedenev.
Thank you.
Okay.
I'm grateful to the organizers for the invitation. Today I'm going to present the talk on the security of some crypto systems based on subfield images of codes. This is joint work with my research advisor Yuri Kosolapov. Well, let's begin. Here you can see the brief outline. We are going to start with some necessary preliminaries on block codes, on subfield images of codes. Then we are going to present key recovery attacks on two crypto systems, namely XJRS crypto system and Ivanov-Krug-Zablov crypto system. And finally, we will discuss how these attacks can be avoided by using U+V constructions for block codes. Let's see what the background is. Classic McAleese has a large public key sizes. Bike and HQC, other finalists of NIST PQ, have some decoding failure rate, so it's harder to prove CCA security. So in order to overcome large public key sizes and presence of DFR, there were attempts to use algebraic codes, namely Reed-Muller codes, Reed-Solomon codes, and algebraic geometry codes. But most of these variants were proved insecure. So using algebraic codes is still desirable, and in order to do this, new protocols have been proposed, namely, for example, Berger-Lloyd rule, RLCE, BBCRS, but these protocols are also were attacked. So recently, protocols based on subfield images of GRS codes have been proposed, and here you can see these protocols: XJRS, Ivanov-Krug-Zablov, and Berger et al. Our goal in this talk is to attack XJRS and Ivanov-Krug-Zablov, and Berger's protocols is still secure, I guess. So let me recall what the generalized Reed-Solomon codes are. GRS codes are defined as follows. Here you can see they are generator matrix, and it is well known that the dual of GRS code is also a GRS code with same X. X is called the support of GRS codes, and Y and Z are called multiplier of GRS codes. So let's consider the definition of M-block codes. M-block code is simply an additive code over alphabet E, which is M tuples of elements from FQ. We can define block Hamming metric, and M-block codes are of particular interest due to ability to correct error burst. By STIL, we define the set of synchronous error burst, and by E, we denote the set of non-synchronous error bursts. And it is well known that M-block code can correct any error from this set, and any synchronous error from this set, and any non-synchronous error from this set. Some block codes with known parameters can be obtained from linear codes over extension fields. Namely, let be a basis of let be FQ basis of an extension field. By phi b we define the map where that for any element produces the coordinates, and by large phi, we define the map that is applied to every coordinate of some vector of length n. So the subfield image of a code relative to the basis is simply defined as follows. And as I said, the parameters are well known. That's it. And other types of block codes can be obtained by the generator and parity checked matrices are given as follows, and the other m block codes with known parameters are generalized subspace subcodes. So you can see the definition of generalized subspace subcode in the slide. We take some subspaces, and the generalized subspace subcode is just this intersection. Generalized subspace subcodes have short representation, namely, since these subspaces can generally have lower dimension than m, we can define the short representation. This is given as follows. And together with generalized subspace subcodes, there are also generalized projected codes. We take just some projection matrices, and generalized projection code is defined as follows. And there is a theorem that establish a connection between between short representation of generalized subspace subcodes and generalized projection codes. Now let's consider XGRS cryptosystem. Key generation. We choose a primitive element gamma of the extension field. We choose the support and the multiplier of generalized Reed-Solomon codes. We then take some parity check matrix of this code, and we also generate a tuple. First tuple is of indices from 1 to n. Each j is of size lambda, and also we generate the invertible matrices of size lambda. And the public key is generated as follows. We take a matrix of subfield image of the code C, and multiply this matrix by block diagonal matrix. So the public key is defined as follows, and the secret key is defined is also in the slide. We propose the following attack. First, we note that if we take any h from this space, it turns out that the resulting column vector is original column vector multiplied by some field element. So it turns out that we can obtain a parity check matrix of some code C prime, which is monomially equivalent to C. And hence we can apply Sidельnikov-Shestakov attack to recover a support of the Reed-Solomon codes, of underlying Reed-Solomon code. So it remains to recover the matrices n. So first we notice that CPUB is generalized, is short representation of generalized subspace subcode, and hence we can try finding the matrices n by solving this linear equation. You can see that this restores long representation of GSS subcode. This returns us to the extension field, and since this code is is a subcode of the original code, then we can multiply it by parity check matrix, and we should obtain now 0. So by solving this equation, we obtain an alternative secret key. And some remarks. First, we assume that gamma is known. The primitive root gamma is known. However, if it is not known, it is no problem to brute force over all the possible gammas. And also, we note that this attack works for any lambda. So, but this attack applies only for original description proposed in the paper. However, a generalized version of XJRS was constructed and attacked by Kirill and Lekane, and it required that lambda is greater than m divided by 2. Now let's move to Ivanov-Krug-Zablov protocol. Here you can see the key generation. We choose some Reed-Solomon code. We choose a random matrix S over a smaller field. We choose m by m non-singular matrices. We choose matrices m of the following sizes. And the public key is S multiplied by the generator matrix of subfield image of RS code, and multiplied by y multiplied by m. So m provides mixing of columns, so the resulting code is not equivalent to subfield image of Reed-Solomon codes. So the secret key is X, S, and Q, defined as follows. Encryption is performed by this formula, and we note the following. In the original paper, it was conjectured that information set decoding attack are harder than for just in the original paper, the authors have overestimated the complexity of ISD attack, and it turns out that we can consider the public code as an M-block code, and the probability of finding the information set is as follows. So actually, this protocol gives no benefit in terms of key sizes. Now let's consider the first attack. First, we partition the public matrix into the blocks. When we take the blocks with odd indices, we note that this matrix G odd is the parity check matrix of short represented generalized subspace subcodes, and we can apply Kirill attack to recover the partial support. For simplicity, we assume that x prime is equals x odd. Now we take x odd and we add the block with some even number, for example 2, 4, and so on. And we also note that this is a parity check matrix of generalized subspace subcodes, subcode, and it turns out that we can recover xi by solving this equation again. So we just brute force xi and see and check whether this equation have whether this linear system has a non-zero solution. If it does, then xi is found. So this allows us to recover the full support of the underlying code, and once the full support is recovered, we can recover the remaining parts of the secret key, also by solving the linear system. And so we obtain an secret key for the IKZ protocol. And let's consider another attack. This attack will work on any code, on any underlying code. It allows to recover the code over the field extension. So to perform the attack, we have to shorten the public code on 2m blocks until obtaining a code of FQ dimension m. Then we puncture the resulting code to keep only one 2m block. It turns out that the resulting code is of the following form, where tiny is a code over field extension of dimension 1, and in order to recover Ri, we can just try brute forcing. First, we note that Ri can be represented as follows, and by brute forcing and trying to recover tiny, we can find the right one. So once one matrix Ri is found, we can find all the errors by restarting the same procedure. So here is how this attack is performed. And let's discuss how these attacks can be avoided. So we really want the block codes with known parameters, but we don't want subfield images and subcodes of subfield images. And it is possible to apply generalized U plus V construction for the block codes. Namely, we choose some m block codes and some diagonal matrices, and we can define the product of m block codes as follows. So it turns out that the parameters of this code are known, and the decoding can be performed as follows. And such codes are not equivalent to any subfield image of codes over extension field, and also these codes are not subcodes of such codes. So it is possible to use such codes to avoid the proposed attacks. So the conclusion: we have developed a key recovery attack on original XJRS cryptosystem. We also have developed a key recovery attack on Ivanov-Krug-Zyablov cryptosystem. And we also discussed how these attacks can be avoided by applying U plus V construction for block codes itself. If you have any questions, well, I'd be glad to answer. Thank you for your attention.
So, who has questions?
So, Kirill, you're discussing about first the two key recovery attacks.
Yeah.
And then you're proposing something which will not work on the U plus V construction. But how big is the confidence after so many of generalized Reed-Solomon cryptosystems in a least setup have in
Well, actually, yeah, no confidence at all. Yeah, we of course, and some further research is needed to obtain some confidence, if any.
In the tennis world, you know this famous saying, no one beats Vitas Gerulaitis 17 times in a row.
Sorry, I didn't hear.
There is a saying in the tennis sport, because he tried to beat Jimmy Connor 16 times, he lost. At the end, he succeeded the 17 times. Maybe someone will construct something with generalized and so on goes at the end successfully, but
yeah.
there is a lack of confidence.
Yeah, and when we talk about expanded code, it could be more beneficial to consider other classes of codes. For example, it can be possible that using BCH codes over some field extension could provide shorter keys in when we consider subfield images. Since Reed-Solomon codes require larger field and larger field when considering subfield images produces bigger keys, so probably also some considering codes of a smaller field can be beneficial. Could be beneficial, yeah.
So if there are no more questions, this concludes this session.
Thank you.